It's paper 3 from May of 2014. Problem number 1. We're given two functions, f of x and g of x. And the first thing we want to show is that f prime of x is equal to g of x. Well, f of x is e to the x plus e to the negative x over 2. Now you don't have to treat that like a quotient because 2 is just a constant. So we're going to take the derivative of this and show that it equals g of x. Well, the derivative, f prime of x, is equal to e to the x, it's always itself, plus e to the negative x is itself, times the derivative of the power, which is negative 1. And that's all over 2. Well, of course, that cleans up to e to the x minus e to the negative x over 2, which is absolutely g of x. So that was pretty easy. Now let's do g prime of x equal to f of x. Well, g of x is given as e to the x, subtract e to the negative x over 2. Derivative, e to the x itself again, e to the negative x itself, multiplied by the derivative of the power, which is negative 1. Let me scoot that subtraction over a little bit. Okay, derivative of the power, negative 1, all over 2. The two negatives become positive, e to the x plus e to the negative x over 2, which is equal to, guess what, f of x. Yay, part 1A is done, 2 marks. All right, part B, we want to write the first 3 non-zero terms in the Maclaurin expansion of f of x. So let me get my magic eraser here and get this stuff out of the way. It's not erasing real fast, so let me speed this up. Select, delete, there we go. So for the Maclaurin expansion, what we're going to need, well, let me write out. This is on your formula sheet, you know. A power expansion is the function, the zero derivative of the function is what I like to call it, times x to the 0 over 0 factorial, and then the numbers just keep going up. So first derivative of x, x to the first over 1 factorial, plus second derivative of the function times x to the second over 2 factorial, etc. You get the idea. So what we need are some derivatives of f. Now it says the first non-zero terms, so we'll have to go until it may take more than 3 derivatives or 2 derivatives. We'll find out. So first of all, let's write down f of x again, which is e to the x plus e to the negative x, all over 2. And since it's Maclaurin, we know this is centered around 0, so we want f of 0. So if you plug 0 in there, you get e to the 0, which is 1, plus e to the negative 0, which is still 1 over 2. 2 over 2 is 1. So there's our value of f0 derivative of x. Okay, taking the first derivative, well, we already know that the first derivative, we just proved it, the first derivative of f of x is equal to g of x, so it's e to the x minus e to the negative x over 2. Plugging in 0 into that, f prime of 0 is 1 minus 1 over 2, and that's equal to 0. So there's that 0 term, so we're not going to be able to use that one. Let's create a new column over here and take the third derivative. Whoops, almost forgot the second. Second derivative, well, as you can see, it just keeps going back and forth. Because f prime of x is g of x, and then you take the derivative again, you're going to be back to f of x. So it's just the first one again. It's the same as this one. So that one is going to be 1, and the pattern continues. The third derivative of x is going to be 0. The fourth derivative of x is going to be 1 again. So now we have our first 3 non-zero terms. Let me highlight those. We've got this one, f of x, and then f double prime of x, and then fourth derivative. So we're ready to write out our Maclaurin expansion using those 3 things. Scrolling down a little bit, I can squeeze it in, I think. So using the power formula, form is f0 of x, which is 1, x to the 0 over 0 factorial, and then we know the next one is 0, so we skip to our second derivative, which is 1, x to the second over 2 factorial, plus, skipping the 0, going to the third yellow highlighted one. That's the fourth derivative. So it's x to the fourth over 4 factorial. And let me clean that up. X to the 0 is 1. X squared over 2 factorial is x squared over 2. And then x to the fourth over 4 factorial is 24. So we have the first 3 non-zero terms in the Maclaurin expansion of f of x. Circled and done. Part B. All right, part C. Hence. Love the word hence. Hence, find the limit. See, hence means using your previous steps. So how do we find the limit of 1 minus f of x over x squared? Okay, let me get this junk out of here and create some room again. Circle, delete. Here we go. Well, I'll just have to memorize what I had hence. So here goes. The limit as x approaches 0 of 1 minus f of x over x squared. Well, f of x, I'm not going to use the original f of x. I'm going to use, hence, the Maclaurin expansion to replace f of x with it. So this would be the limit as x approaches 0 of 1 minus that expansion. Now, we only did the first 3 terms, but what we'll do, we'll show that that pattern continues. I'll just go dot, 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 because you'll see what happens here. All over x squared. So, cleaning that up. All we have is a negative in front of a set of parentheses, so it's 1 minus 1. That drops out, and then everything else is going to be negative, so negative x squared over 2, negative x to the fourth over 24, etc. The pattern continues. You're going to have a negative x to an even exponent. I mean, you can see that pattern all over x squared. So we can cancel, or you could say you're going to factor out on the top. You're going to factor out a negative x squared, or I'll just show the cancellation. That cancels with that, leaving a 1, and it cancels with that, leaving an x squared, and then the next one would be x to the fourth. So the rest of the terms after this first term, there's the first term, the rest of them, you're going to have an x squared on the top, and you're taking the limit as x approaches 0. So those are all going to become zeros. The only thing you're going to be left with is equal to negative 1 over 2, which is negative 1/2. And hence, we have found the value of that limit. And the answer is negative 1/2. Okay, now for part D. Find the value of the improper integral, which goes from 0 to infinity of g of x. G of x originally was given as e to the x minus e to the negative x over 2 over f of x squared. Well, what I'm going to do is, I'm just going to, since it's over, I'm going to multiply by the reciprocal of f of x squared. And f of x was 2 over e to the x plus e to the negative x. Now we're going to square that, dx. Alright, this looks a little messy, but let's go in for the cleanup here. 0 to infinity. First thing I want to do is square that second set of parentheses. So let me rewrite this first stuff. So the 2 squared is 4, of course. And the denominator squared. I don't think I'll square that out. I think I'll just leave it, e to the x plus e to the negative x squared, because I see a u substitution coming on here. And our 2 and the 4 cancels with the 2, and let's kick that out front. So we have 2 times the integral from 0 to infinity, e to the x minus e to the negative x over e to the x plus e to the negative x squared dx. Now, they kind of lead you into this. If you notice that denominator, we've messed with that a couple of times already. And when you take the derivative of that, the only thing that changes is the sign separating. So that's going to be the numerator. So what I'm leading up to, yeah, we're going to use u substitution, let u equal what's in the denominator before we square it. So let's come over here. U equals e to the x plus e to the negative x. So the derivative of that is going to be e to the x minus e to the negative x. And we're going to solve that for dx. So dx equals, remember that always reciprocates, so du over e to the x minus e to the negative x. All right, let's use all that and rewrite our integral. So we're going to go from 2 times the integral, and I'm not going to put in my limits because they've changed now that I'm using u. I'll put those back in later. So the numerator is still there temporarily, minus e to the negative x. We didn't mess with that yet. The denominator is now u, because that's what we let u equal, squared. Dx is now du over e to the x minus e to the negative x. All right, fun part, cancel. It's gone. So all we've got now is 2 times the integral of 1 over u squared, or u to the negative 2, if you want to think of it as that. Integrate that. Of course, we increase over the new power. So that's going to be 2 times 1 over u to the first. Make that negative. Yes, yes, yes. It was u to the negative 1. So we put the new power on the bottom, or flip that negative 1 to the top. So our final result then is negative 2 over u. Now let's put our u value back in. So that's negative 2 over our original u was e to the x plus e to the negative x. All right, our limits of integration, 0 to pi, and now we have to evaluate that. Well, the easier one to do, let's do the denominator first. Let me come back over here to the left. E to the x plus e to the negative x, infinity from 0. If you put a 0 in there on the bottom, you get e to the 0 plus e to the 0, which is 2. So we get negative 2 over 2, which is negative 1. Okay, now the top. Here comes the tricky part. When we put infinity in, we're going to get negative 2 over e to the infinity plus e to the negative infinity, or 1 over e to the infinity. Well, that gets to be a little messy. And that really is not that difficult to visualize what's going on, because that equals negative 2 on the top. And on the bottom, remember, 1 over e to the infinity, the denominator is getting extremely large, so that part is approaching 0. So we've got negative 2 over e to the infinity. And since, again, e to the infinity is extremely large, this whole fraction as a limit is going to be approaching 0. So the top value of this integral is going to be 0, and then when we subtract those two to evaluate the integral, we get 1. So since the integral has a value of 1, it does converge, and that is the answer. And this one is done.